The title of this report is Temperature Change Generated Longitudinal Fracture of Inhomogeneous Bars with Fixed Supports. Continuously inhomogeneous structural materials are characterized by smooth change of their properties in a solid. The most typical examples in this relation are the functionally graded materials, which have a quickly growing use in a variety of structural applications in the up-to-date engineering. In many cases, different continuously inhomogeneous structural members are subjected to temperature change that may have significant influence on the structural integrity. This paper aims to clarify how the longitudinal fracture of continuously inhomogeneous bars with fixed supports is affected by temperature change. In particular, we considered a bar with circular cross-section. The material is continuously inhomogeneous along the bar length. The bar has two portions with different radius. Besides, the bar hosts a longitudinal crack representing a circular cylindrical surface. Due to the fact that the bar is statically indeterminate structure, the temperature change to which the bar is subjected induces stresses that have influence on the longitudinal fracture. The problem of the strain energy release rate in the bar is solved. An approach from the literature is used for check. Since the bar has nonlinear elastic behavior under temperature change, the complementary strain energy is used for deriving the strain energy release rate. A variety of graphs revealing the influence of the temperature change and other parameters of the bar model on the strain energy release rate are presented. The bar studied in this paper is depicted in figure number 1. The cross-section of the bar is a circle. The bar has two portions, L1, L2, and L2, L4, with different radii, namely R1 and R2. Furthermore, the bar hosts a longitudinal crack with length A in portion L2, L3. The crack represents a circular cylindrical surface with radius R1. The crack front is in bar section L3. The bar is under uniformly distributed temperature change. Both supports of the bar are fixed. Therefore, the bar is statically indeterminate system. The mechanical behavior of the bar is nonlinear elastic and is treated by the constitutive law given in equation number 1. Here, sigma and epsilon are the stress and strain. D and Q are material parameters. Since the material is continuously inhomogeneous along the bar length, D and Q change smoothly along the axis X, as given in equations number 2 and 3. In these equations, dl1 and dl4 are the values of D in sections L1 and L4 of the bar. QL1 and QL4 are the values of Q in the corresponding sections. Beta and delta are parameters. The origin of axis X is in section L1. The coefficient of thermal expansion also changes smoothly along the bar length. Equation number 5 describes the change of alpha t along the axis x. Here, alpha TL1 and alpha TL4 are the values of alpha T in sections L1 and L4 of the bar. Lambda is a parameter. Since both supports of the bar are fixed, the uniformly distributed temperature change induces an axial force. The mutual axial displacement of the bar end sections L1 and L4 is zero. Here is zero as shown in figure number 7. Here delta L1, L3 and delta L3, L4 are the prolongations of bar portions L1, L3 and L3, L4 respectively. They are obtained by using equations number 9 and 10. Here, delta L1, L3T and delta L3, L4T are the prolongations due to temperature change and prolongations induced by the axial forces. The prolongations are evaluated by applying equations from number 11 to number 14. In these equations, epsilon L1, L3 and epsilon L3, L4 are the strains in portions L1, L3 and L3, L4 of the bar. Then we transform equations number 9 and 10 as given in equations number 15 and 16. The strains are expressed as functions of stresses using equation number 1 as given in equations number 17 and 18. Then by using equations number 8, 15, 16, 17 and 18, we transform equation number 7 as given in equation number 19. Since the bar is in equilibrium, the axial forces N, L3, L4 and L, L3, L4 in portions L1, L3 and L3, L4 of the bar are equal as given in equation number 20. The axial forces are presented as functions of stresses by applying equations number 21 and 22. Then equation number 19 is transformed as given in equation number 23. From the fact that the stresses induced by the axial forces are distributed uniformly in the bar cross-section, it follows that equation number 23 can be rewritten as given in equation number 24. Here, the cross-section areas are given in equations number 25 and number 26. The strain energy release rate in the nonlinear elastic bar is obtained by applying equation number 27. Here, U asterisk is the complementary strain energy in the bar structure. The quantity dAcr is given in equation number 28. Here, dA is an elementary growth in the length of the delamination crack. Therefore, we can replace equation 27 by equation number 29. The complementary strain energy is determined by applying equation number 30. The complementary strain energy in portions L1, L3 is evaluated by applying equation number 31. The density of the complementary strain energy is defined by using equation number 32. Analogically, for the complementary strain energy in portion L3, L4 of the bar, we have equations number 33 and 34. For check, the strain energy release rate is also evaluated by using the expression given in equation number 35. This is known from the literature and is used here for checkup of the solution. Equation number 35 gives the strain energy release rate, which corresponds to the strain energy release rate derived by applying equation number 29. It is analyzed here how the strain energy release rate is influenced by the temperature changes and other parameters of the bar theoretical model. It is also demonstrated how the analysis can be applied in design of structures subjected to temperature change. For instance, to determine the radius of the bar cross-section. Figures number 2, 3, and 4 illustrate the influence of various parameters on the strain energy release rate established by the analysis. Strain energy release rate is shown in dimensionless form. Determination of the radius is illustrated in figure number 5. First, the influence of the change of the coefficient of thermal expansion along the bar length on the strain energy release rate is analyzed. The influence of the change of the parameter dL1 on the strain energy release rate is analyzed too. These influences are illustrated in figure number 2, where the relation between the strain energy release rate and alpha T L4 to alpha T L1 ratio is plotted at 3 dL4 to dL1 ratios. In figure number 2, we observe a growth of the strain energy release rate with a rise in alpha TL4 to alpha TL1 ratio. A growth in the strain energy release rate with increasing ratio dL4 to dL1 is also observed. The following is an analysis of the influence of the temperature change in the rod on the strain energy release rate in relation to the ratio A to L2. In this regard, strain energy release rate is plotted against temperature in figure number 3 at 3 A to L2 ratios. A significant increase in the strain energy release rate resulting from temperature rise can be seen in figure number 3. An increase in strain energy release rate as a result of increasing of A to L2 ratio can also be seen in figure number 3. Next, the influence of bar geometry and change of the parameter Q in the bar longitudinal direction on the strain energy release rate are analyzed via L2 to L1 ratio and QL4 to QL1 ratios. Figure number 4 shows the variation of strain energy release rate with increasing L2 to L1 ratio at 3 QL4 to QL1 ratios. We observe also that strain energy release rate rises smoothly with rise of L2 to L1 ratio in figure number 4.
Professor,
Finally,
sorry, time.
okay, I will finish soon. Finally, we demonstrate to determine the radius of the cross section of the bar in portion L2 to L4 based on fracture mechanics. In this regard, the variation of the strain energy release rate with rise of R2 to R1 ratio is depicted in figure number 5. The ratio at which the strain energy release rate reaches the fracture toughness of the material is used to determine the desired radius of the cross section. It can be summarized that the analysis presented in this paper can be applied in structural design of such a continuously inhomogeneous structure subjected to uniform temperature change with considering the material nonlinearity. Thank you for your attention. If you have questions, I will try to answer.